Tonight's Chapter 5, Topologies and Ethernet Standards. So we'll talk about the basic and hybrid LAN physical topologies and as well as logical topologies. This book does a pretty good job of drawing a distinction between the two. Most of the time when you look at a textbook or you look at most books and they talk about topologies, they don't make a distinction between the two, and they're not really very clear about the differences of why it's important to look at one versus the other. Every LAN has both a logical and a physical topology. Usually when you don't see a specific reference to one or the other, they're usually talking about physical topology, but there is a distinction between the two, and this book does a pretty good job of making that distinction. I'll talk a little bit about backbone structures that form the foundation of most LANs, transmission methods underlying Ethernet networks, how Ethernet actually processes messages, how it handles collisions and things like that. And then the chapter finishes up talking about switching and data transmissions. So physical topology. How are the nodes physically laid out? How are they physically related to each other? How are they connected and how are they physically related? So you're really looking at kind of a broad scope of your network. You're not really talking about the specific technologies that are being used, whether or not it's Ethernet or token ring or any of that type of stuff. You're not worried about the physical cables, whether it's fiber or shielded twisted pair or unshielded twisted pair. You're not getting that specific at this point. You're just trying to denote physically how these various devices are connected. So you're not specifying this stuff right in here. The fundamental types when we talk about physical topology are bus, ring, star, and then in reality usually you end up with more of a hybrid, especially once the network starts to grow in size a little bit. Bus topology has been around a long time. It's a very simple approach. It's literally just connecting kind of in a daisy chain, one computer to the next, to the next, to the next. One of the advantages of that approach, it doesn't require a lot of cabling. It requires less than, say, a star topology. So it's relatively cheap because it doesn't require as much cabling. You also don't necessarily have to have any type of networking device, like a hub or a router, a hub or a switch or anything like that. So it can be cheaper, so it's relatively easy to implement. Most of the time in a bus topology, you're going to be using coax cable. It's just the nature of that type of network. It doesn't necessarily have to be, but that's normally what you're going to find. It's a passive topology, and what they mean by that is in a bus physical topology, each node is simply listening to the wire for communication. If that particular communication happens to be destined for it, it listens to it and actually pays attention to what that message has to say. If it's not destined for that particular one, it just ignores it. That's a security concern, because that means if you switch to the networking card in promiscuous mode, you can sit there and listen to all the communications that are running across that wire. So that's a potential security concern using that type of topology. So that's what they're talking about, a broadcast domain. Nodes communicate using broadcast transmission. So all the various nodes on that particular segment can all hear what the other nodes are saying. As far as the wires themselves, the coax cable, they have to be terminated properly. If not, you'll run into a problem with the signals. If it's not terminated properly, the signal will bounce back and forth from end to end of the cable, and will create a broadcast storm where all the network cards are hearing multiple communications sent to them and will bog down the network. Also, you have to terminate the signal using a grounding one end of the cable somewhere along the line. Most of the time, you'll just ground it to a PC that's connected to the network. So that's what a bus physical topology might look like. You've got your grounding terminators on each end. You've got just a basic wire that's going to run from this one to this one to this one to this one to this one, and it'll be grounded somewhere along the way. It doesn't require a lot of cable. That's one of the easy things about it. You've got a small network in an office building that you just want to link several computers together. It's a very quick, easy way to do it without having to invest a lot of money. You won't see these hardly at all anymore. So the advantages, relatively inexpensive. It does not scale well, meaning you add more and more computers because they're all on the same collision domain. You run into a problem as you add more and more computers, you end up with more and more collisions. We'll talk about collisions a little bit more when we get to Ethernet. It's difficult to troubleshoot. If you go back and you end up with a break in the cable somewhere, you're going to have problems, obviously, with your entire network, with all of your computers communicating. Why? Because they're no longer properly terminated. Your bus is no longer properly terminated. And it's not very fault tolerant. Any questions so far? That's one topology. Like I said, you're just not going to run into it that often unless you happen to come into a really old networking situation. They used to be pretty popular because they were cheap to implement. They're just not used that much anymore. A ring topology is exactly what it sounds like. It's done in a ring. A node connects to the nearest two nodes in a circular fashion. So you end up with a circular network. The data can get, depends on how you look at it, whether or not it's clockwise versus counterclockwise. In some situations, you can actually have it where the data flows in both directions. For example, an ATM network, the data works in both directions. It's an active topology, which means the workstation participates in the data delivery. So as the data is going around the ring, it picks up that piece of data and looks at it and says, is this for me? If not, it puts it back on and regenerates that signal and passes it on to the next node. So it's actually participating in the delivery of the data. The advantage to that is it gives you better range. It also cuts down on some of the security issues because it's actually participating in it. So once it's picked up, it's no longer available on the wire. Data stops at its destination. Physical medium. It uses twisted pair or fiber optic cable. You can use coax, but it's less common in tokenry. So it might look physically something like that. Now this one has a similar drawback to it, like bus did. If you end up with a break in the ring somewhere, you're going to have problems with your various nodes communicating, especially if you're on a token ring network that only communicates in one direction. If you've got a break, say right here, this node and this node cannot communicate, because there's no physical connection as far as they're concerned anymore because of the direction. So a malfunctioning workstation can disable the network. It's not flexible or stable. Again, as you add more and more nodes to it, it becomes more problematic. Physically, star is by far the most common approach. As far if you want to kind of narrow it down to one single type of physical topology, the reality is we tend to have more of a hybrid approach as they grow. But we usually start out with the star topology because it gives us a few advantages. There's some disadvantages, but there's a few advantages that kind of outweigh those. The nodes connect through a central device, a hub, a switch, or a router, something like that. Physical medium usually uses twisted pair, especially for smaller networks. If you grow in size, it performs as part of the backbone. You may be using fiber optic, but for the most part, you're going to be using twisted pair. A single cable is used to connect two devices. Connect a node back to that switch or back to that router. The advantage is fault tolerance. If a node goes down, the only thing that's affected is that node. It doesn't affect any other computer on the network. If a cable gets cut, the only thing that's affected is the node that was connected to that cable. None of the other computers are affected. What's the problem with the star approach, star topology?
Single point of failure.
Single point of failure. If your hub or switch goes down, everything's down. So you've got that one device that you really need to make sure stays up and going. Other than that, it's a really good approach. Makes troubleshooting very easy with that approach. So advantages: fault tolerance, central connection point for all affects the LAN segment, and it's very scalable. It's very easy to add additional units or additional nodes to the network. So a star topology might look something like that. That's what you see with Ethernet-based networks. You can potentially have up to 1,024 addressable logical network nodes. Practically speaking, you're never going to see that. You can't have that many different nodes connected to one network without having too many collisions to make the network function. So because of that, we end up having to segment our network so you don't have those types of problems. But theoretically, you can connect that many without having any problems. Logical topologies describe how the data actually flows from one computer to the next. So you can potentially have a star physical topology that that communicates via a bus logically or via a star or a ring logically. And that's what the next few slides kind of talk about. So the most common logical topologies are bus and ring. In a bus topology, signals travel from one device to all the other devices. May or may not travel through intervening connectivity of devices. You may or may not have to have a hub or a switch or whatever. A bus logical topology used by networks with a physical bus topology and a star or a star wired bus topology, such as Ethernet. And I think there's a, yeah, we'll get down to that here in just a second. Ring logical topology, rings follow a circular path, same thing as what you might think of from the physical topology. The ring logical topology is used by networks with a pure ring topology or the star-winged wired ring hybrid physical topology like token ring. So a hybrid physical topologies, a pure bus, ring, and star topologies, you don't really have those in practical applications unless it's a very small network. Very small network, it makes sense to possibly have a star-based topology. But for the most part, if it starts to grow in complexity at all, you're going to kind of have more of a hybrid approach where you might link two star segments together like a bus. So hybrids tend to be more common, but it does add to the complexity of your network. You've got several different options. Now, a star-wired ring has a star physical topology with a ring logical topology. So now this is what you tend to see more in practice. This is a network, a token ring network. The other one we'll go to here in just a second is Ethernet. That's what you're going to see probably most often. The benefit is fault tolerance, and like I said, this is something you see in the token ring. So physically, you have a star typology. You've got a hub or a switch here, and physically, all these different nodes are connected physically like a star. The way things are actually communicated, though, is the data comes out, goes to this node, comes back to your hub or switch, comes out, goes back to this node, and back to the switch or router or whatever. And it does that for each single one. So logically, it's bouncing around from node to node. So the way the data actually travels is a bus topology. Star-wired, that's ring. A star-wired bus, workstation groups that are connected, again, like a star physically, but they're networked via a single bus. The advantage is that it covers longer distances. It's easy to add nodes to the network. The drawback is the cabling, connectivity, device expense, etc. And that's where we see Ethernet networks being used. That's how Ethernet networks are implemented. So you might end up with a switch or router or hub performing in that type of configuration. So any questions over that? How we're tying together logical and physical topologies? Okay, so backbone networks may be nothing more than cabling itself. If it's a small network, it may be a switch. That may be your backbone of your particular network. But for the most part, as networks get larger and larger, we're trying to tie together different LANs together. We need to have some type of high-speed, fault-tolerant method of tying those different networks together. That's what our backbone is. So it's usually going to be Cat6, Cat7 cable, fiber optic, something like that. So backbones are the cabling connecting hubs, switches, and routers to provide more throughput. Why? Because presumably we're seeing a lot of data back and forth from one LAN to another. So we have to have a lot of capacity. Large organizations may be using fiber optic, etc. As it grows, as our need for a backbone grows, it becomes much more complex, much more difficult to be able to tie all those different LANs together. It becomes much more difficult to be able to manage that process. Why? Because in a lot of cases, we don't have control over that cabling. We may have to go to AT&T or Verizon or whoever to be able to lease lines from them in order to be able to have that kind of capacity. As far as the different types of configurations, we've got a serial backbone, which is the simplest one. 2 or more internetworking devices to be able to tie them together in a serial fashion. So we can tie these different devices together. That allows us to stretch out the distance that we have, that we can go from our router ultimately down to our various nodes that are on our network. It's done basically by daisy chaining them together, and the benefit is it gives us a logical growth solution, modular additions. If we need to add more, we can simply add more devices to be able to stretch it out and be able to add more nodes. It's a low-cost LAN infrastructure expansion. Like I said, easy to attach hubs and expand it out. So you can only go so far. I think the rule in a 10 meg network is 543. So 5 devices, or excuse me, 5 segments, 4 devices, 3 populated segments. Serial connection of repeating devices is essential for distance communication. There are standards that define the number of hubs allowed, and the idea is that if we push the limits to those standards, we're going to run into issues. Because as we stretch these out, if these are all 100 meters, say we're running Ethernet, and our segment length is 100 meters, that's the greatest distance you're supposed to have between devices on your network in an Ethernet network. So if that's 100 meters, and that's 100 meters, and that's 100 meters, and this is a 100 meg network, we may be running into problems by stretching things out to their extremes, especially if our backbone is not up to standard. If we're not terminating connections properly, we don't have good shielding on our cables and things like that, that will shorten the distance that we can reliably transmit data. And you'll start to see problems creep into your network if you're not doing that. So you can end up with some of those intermittent and unpredictable transmission errors. A good test for that sometimes is to ping your host periodically and see what's getting through, make sure all your packets are getting through. Any questions so far? Good. There are several different types of structures of distributed backbones. Personally, I like the collapsed backbone because it intuitively makes more sense. We'll get to that here in just a second. Connectivity devices connected to a hierarchy of centrally connective devices. Simple expansion, limited capital outlay. It's trying to keep the cost down, especially as you get into larger networks, higher end switches and routers. The costs will go way up. So it's a more complicated distributed backbone. Allows you to connect multiple LANs and LAN segments using routers. So you've got a basic one here. It's just using switches, and a more complicated one there. And it allows you to, if you need to expand the network, you just add another router over here, more switches. You can add a lot more nodes by doing that. So it gives you a very modular approach to your network. Depends on the needs, obviously which design you want to take. For the most part, you want to avoid routers whenever you can. Why? What layer do the routers operate at?
3.
Yeah. What layer do switches operate at?
2.
Switches operate a lot faster. They don't have to open up packets as far on an OSI model to be able to analyze them to move packets to the next destination. It just opens it up to layer 2, says this isn't the right one, let's go to the next one. So switches operate much faster. So switches operate faster, so we want to use them whenever we can, avoid using routers whenever we can. Distributed backbones, good for work group segregation. May include daisy chain linked hubs. You still have length considerations. Remember, we're limited in the length of our segments. The drawback, again, single point of failure. This is the one I was talking about a minute ago, class backbone. To me, it just intuitively makes the most sense. It's a very hierarchical structure. You've got to, at least at some point in most networks, you've got to have internet connectivity. So you have to have a router at some point. So that you have a central point of failure there with the router, but that's one central point of failure. Other than that, all your different work groups are connected via hubs. Ideally, you connect those with switches. We'll talk about why here in a little bit. But intuitively, it makes a lot of sense. So it uses a router or a switch, single central connection point for multiple subnetworks. The highest layer is going to have a router, presumably with multiple processors. Why? Because there's just one router. It's going to be doing a lot of work. So it can become a point of congestion for the network if there's a lot of activity going on in the network. Advantages: interconnect different subnetwork types and centralized management. Now, if you're really paranoid, your in the banking industry, your finance industry, your a medical facility, the government, you may end up going with something I refer to as a parallel backbone. Something that's going to give you some redundant connections between your various devices on the network. Why? In case a wire gets cut somewhere along the ways, you can continue to have connectivity between devices. So it tends to be more robust. Requires duplicate connections between connectivity devices. So you've got all those redundant links, increased performance. Why? Because you've got 2 links to every device. So better fault tolerance. So you end up with dual connections between your routers and your switches. All your main connections end up with dual routes. The problem is a lot more cabling. Your costs are going to go up because of that. But if you happen to have a critical infrastructure that needs to be up and running all the time, that needs that type of performance, it might make sense to do something like that. So that's it so far for that type of stuff. Any questions yet? We're going to switch over into switching and talk about some of the ideas behind switching.
Is there any reason they still teach or still have hubs on their curriculum?
Pardon?
Is there any reason they still have hubs on their curriculum?
I think they just do it. Most textbooks will talk about hubs a little bit, just because that's kind of the history side of networking. Without that, you don't really have the idea of what broadcast domains are or collision domains are. Switches alleviate a lot of those problems.
Right. I mean, they're just worthless.
Yeah, they are, and you're not going to see them hardly anywhere.
Because a switch now is just almost the same process a hub used to be.
But a switch operates at a higher level.
Probably, but just the cost-wise, though, is still there.
Yeah, I mean, you might have to go to eBay to find an old hub. I don't know that anybody sells a hub anymore. But I think from a theory perspective, like I said, you don't have broadcast, tend to have broadcast domains or broadcast issues like you did with hubs or collision domains that you had with hubs. It's not nearly as big a problem as what you have. So I think from a theory side of things, that's why they tend to want to talk about them, just to kind of show you the evolution from hubs to switches to routers. Switching, logical network topology component. So it's something that operates at layer 2 of the OSI model, as opposed to hubs which operate at layer 1. So it does a little bit of processing of the packets as it's coming through. A hub is literally just sending out the information. It gets information and sends it back out to all the nodes. It's not bothering to look at any of the information that's coming into it, one of its ports. It's just blindly sending it out to all the other ports on the network. That's why you run into collision, create collisions and things like that, because all the data is being sent over all the various wires on the network because of the way a hub operates. Switching operates a little bit differently than that. Switching operates at layer 2 and allows you to open up the packet a little bit and look at the MAC address of the packet that it's coming into, or excuse me, of the computer that it's coming into, and the computer that it's going out to. So a little bit of intelligence going on when we talk about switching. 3 methods of switching. For the most part, you're only going to be talking about 2, circuit switching and packet switching. They toss in something referred to as message switching, but you're not really going to ever hear about that. Like I said, for the most part, you hear about circuit switching, which is a traditional form of switching, and then packet switching. So with circuit switching, that's what they used to do with telephone networks. When you made a call, you picked up the telephone, they physically connected a circuit between you and whoever it was you were calling. That was a single circuit. It was dedicated to you. The downside to that was when you're not talking, you're wasting bandwidth. If you pause for a second, you're wasting bandwidth. It's still dedicated to you because that's your circuit for the duration of that call. But that was one of the downsides of it. That's your dedicated circuit for the duration of your call. It may be appropriate in some situations. If you're doing video conferencing, for example, you want to have that dedicated bandwidth so you're not having to share it with other people. So there are times when you might want to have a dedicated circuit, but you do tend to have a lot of wasted resources. Message switching is kind of a compromise between the two. You send out a message, it opens up a connection, you send out a message, you close the connection. If you need to then receive a message back from the same place, or send another message out, you do the whole thing, the same thing over again. It may or may not be the same circuit that you just had. So you spend a lot of time with overhead with message switching, just in establishing and closing down connections back and forth. Packet switching is what we see today on digital networks or on digital networks. It breaks down the data into packets before it's transported. So as we send a message out, it breaks every message down into packets and adds additional information to it, such as header information, destination address, delivery address, error checking information, things like that, to be able to deliver that packet to where its destination is. And since it's breaking up that message, it's got to have a way of getting that message from point A to point B. It may or may not take the same path. That's the advantage of packet switching. Why? Because the status of circuits change over time. And we're not talking about days, we're talking about milliseconds. So as a router becomes busier, it may not be able to process as many messages. So instead of taking that particular route, it might be more efficient for the next packet to take a different route. Well, that means on the receiving side of things, packets may not arrive in the exact same order. That's why it's important to have a sequence number on your various packets, so that on the receiving side, you can look at the sequence number and reassemble the messages, reassemble the packets back into their original order, so you can have your message on the receiving side reassembled. Reassemble at destination requires speedy connections for live audio-video transmission. This is something where you start to see newer routers, for example, be able to handle quality of service issues and prioritize certain types of packets over other types of packets to be able to try to address some of those needs of audio and video delivery. So advantages of packet switching, everybody's sharing that bandwidth. So as you talk less, somebody else can talk more. I say talk, send data, whatever it happens to be. As you talk more, somebody somewhere is talking less. Everybody's kind of sharing the same medium. Devices do not process information. Examples, Ethernet networks and the internet. MPLS is another type of switching. It's not something you're going to see a lot unless you're working with Cisco routers or Cisco switches. Cisco switches use this approach. An advantage to it, multiple layer 3 protocols. It supports IP, so you can actually, talks about packet switching. Actually, that's a different thing. Supports IP, common use layer 2 WAN protocols. We'll come back to this here in just a little bit. Yeah. Okay, so advantages: use packet switch technologies over traditionally circuit switched networks. Creates end-to-end paths. Addresses traditional packet switching limitations and provides better quality of service, which is what I was talking about earlier. So if you happen to have a network where you've got mixed types of communication, email, video and voice, file sharing, etc., it's not quite as important for file sharing files, packets to go from point A to point B as quickly as it is for your video and voice communications. So you can address that by setting your quality of service to appropriate levels for a particular protocol that allows those packets to be prioritized over other packets. And it does that by putting in what they call a shim between layer 2 and layer 3, and allows the switch to be able to process that more quickly than if it was actually having to process at layer 3. Ethernet. Any questions on that? Ethernet is kind of an interesting thing. It's been around a very long time. I know that young people sometimes look at technology today and think, you old people don't know what you're talking about, and I kind of throw myself in that. I'm not that old. The Ethernet's been around a long time. Xerox developed it back in the 70s. Xerox didn't know what they developed. They developed the mouse, the graphical user interface, the laser printer, Ethernet. They developed a lot of stuff out there at Xerox. What they didn't have was the business savvy, if you will, to be able to apply it in a business setting. Benefits of Ethernet: it's very flexible, good throughput for a reasonable cost, popular network technology. All variations share a common access method called CSMA/CD. carrier sense multiple access / collision detected. And that's true of all wire-based Ethernet. Some people will talk about wireless being Ethernet-based, and it is. It's slightly different. It's CSMA / CA, collision avoidance. So it operates slightly differently. We'll talk about that a little bit more when we get to the wireless chapter. So carrier sense multiple access collision detected. If we are using hubs, which is going back to your point earlier, if we're using hubs, when a request is sent from one PC for a file from another PC, it broadcasts that request. It sends that request to the hub, which broadcasts that request to all the computers on the network. That creates a lot of traffic. That's a problem. Ethernet uses carrier sense multiple access collision detection as a way to try to address those problems. So the first thing that Ethernet does is it listens to the wire to say, is anybody talking? Is there any noise occurring on the network? That's the carrier sense part. So if there's nothing occurring, or if there is something occurring, it waits. It says, okay, I'll wait to send my message for a little bit of time. If there is nothing going on in the network, it'll go ahead and broadcast that message or send that message out to the hub. Hub will then broadcast it back out. So if there is additional stuff going on in the network, there is multiple access, it waits. Once it's sent that, if it detects a collision, it sends out a jamming signal. Says, whoa, 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 hold up. Everybody hold up. Let's back up. There's a problem with that. We had a collision. And it waits a random amount of time to then rebroadcast, retransmit that information. So it goes through that process until ultimately it's successful at sending that message. And that's what all that is. The problem with that is in heavily trafficked network segments, the number of collisions goes way up. That's why hubs really are only suitable for very small networks. Given the prices of switches, the prices of routers relative to the prices of hubs anymore, nobody uses a hub. I don't, like I was saying earlier, I don't know that anybody sells hubs anymore. You might have to go to Smithsonian to see one. So physically, it may look exactly like a switch. You plug in network cables, it's an 8-port switch or an RJ45 plug. It may look like a switch, but it's how it processes the information that's coming into it and sending it back out that is the distinction. So segment growth, as the number of nodes on your network segment grows, the more a problem collisions become, the bigger the issue is. Collisions corrupt data, truncate data frames, etc. The network has to compensate for them. How does it compensate for them? If a packet doesn't make it to its destination, what happens?
Drops it.
It drops it. What has to happen when it gets dropped?
It's to be resent.
It's got to be resent. You've already got a network that started bogging down because of too many transmissions. Having to resend packets just kind of exacerbates the problem. So that's kind of a flow chart, if you will, of how carrier sense multiple access collision detection actually works. So the station listens for activity. If it detects activity, then it waits. If it doesn't, it'll go ahead and transmit it. Once it's transmitted, if it detects a collision, it's going to stop transmitting and jam it and start the process over again. If it doesn't detect a collision, then the transmission went through fine. So that collision domain is the portion of the network where collisions occur. Again, if you get rid of a hub, you go to a switch, you drastically reduce that. I won't say you eliminate the possibility of collisions, but you drastically reduce the number of collisions that you're going to have. Ethernet network designed repeaters repeat collisions, so simply having repeaters on the network doesn't help. In fact, it increases your collision domain. Switches and routers, however, separate those collision domains into individual circuits, so the chances of having collision are much, much less. I also draw the distinction between a collision domain and a broadcast domain. A collision domain is never bigger than the broadcast domain. It may be as big, depending on how you have your network segmented, but it's never going to be bigger than your broadcast domain. Okay. Ethernet cabling distance limitation is affected by the collision domain. So the further out you have stretched your network, the bigger your collision domain potentially can be. Why? because of this issue right here, data propagation. That's the time that it takes for data to travel from one segment point to another. If it's too long, if you stressed out your network segments too long, now all of a sudden you can't accurately identify when a collision has occurred versus when it hasn't. So now all of a sudden you are assuming that there was no collision detected when in fact there may have been, but you weren't able to detect it because your nodes are spread out too far. So that can become an issue, especially if you're not paying attention to your number of segments that you're allowed and the speed of your network. So with a 10 meg network, which is a very old network, you don't see a lot of those anymore, you can have that 543 rule, 5 segments connected with 4 hubs, 3 of them populated. But you can't do that with a 100 megabit network, where you can only have 3 segments, 2 connected hubs. Okay, Ethernet standards for copper cable. You can run Ethernet across copper, you can run Ethernet across fiber. There's several different ways. It's not dependent upon the medium that you're running it on. As far as the copper standards, IEEE has developed standards on how to transmit that data across the media, and it differs significantly in signal encoding depending on the specific Ethernet standard. We've got 10 meg, 100 meg, gigabit, 10 gigabit. So depending on which standard we're talking about, the encoding is slightly different. That all affects the throughput, the segment length, as well as the wiring requirements. So the oldest Ethernet, 10 base T. 10 stands for the 10 megabit. That's how fast it can send data down the wire, 10 megabits per second. Base stands for baseband. So it's going to use that entire bandwidth of that particular medium. And T stands for twisted pair. So that's what they're talking about when that's what the breakdown is. And we'll skip ahead just for a second to give you an example of 100 base T. It's the same exact format. 100 megabits per second, baseband, T is for twisted pair. So again, baseband transmission, T for twisted pair. Uses 2 pairs of wires to transmit and receive. So it's full duplex. You've got a total of 4 pairs of wire, 8 wires. But it's only using 2 pairs. 2 pairs are going unused. For the most part, that's true of all the standards until we get into gigabit. Follows the 543 rule of networking, so 5 network segments, 4 repeating devices, 3 populated segments maximum. So, given the 543 rule here that they're showing, what's the maximum distance that you can have between 2 nodes? Not accounting for the width of a switch or PC.
It's 100 meters.
The maximum distance between, say, node A, workstation A, and workstation B, 500 meters would be the maximum. So 100 meters between the hub and the node, 100 meters between the hub and this hub, and then finally here. That's as far as you can stretch them out using that rule of thumb. With 100 base T, it's pretty similar to 10 base T, also baseband transmission, star topology, RJ45. So it may look exactly the same. You're not going to be able to tell the difference just by looking at it without seeing some kind of numbers. Supports 3 network segments connected with 2 repeating devices, again still at 100 meters. We've got 100 base TX, 100 megabits of throughput over twisted pair. Full duplex transmission doubles the effective bandwidth. So in this case, you've only got 2 repeating devices and 3 segments. So now the furthest they can be apart is 300 meters. So because that's the trade-off that we're making, for that increased speed, significant increase in speed, we're shortening the distance between 2 nodes in our LAN. To be able to get a greater distance, we're going to have to consider using different cabling, different networking devices to be able to do that. Fiber optic, for example, that we'll talk about in a moment. 1000 base T or gigabit Ethernet. Again, 1000 represents the speed, 1000 megabits per second, baseband, twisted pair. That uses all 4 pairs of wiring. So, actually, I should have gone back. The 100 base T also requires Cat5. With 10 base T, you can get by with Cat3, actually. Data encoding schemes different for 100 base T, meaning that there's not a direct translation. So if you mix 100 base T network on a 1,000 base network, it's going to slow down to the 100 meg network, 100 base T network. So you can combine the standards. The maximum segment length on a gigabit network is 100 meters. So you're shrinking that down significantly. And then you're not going to see a lot of those anymore, or a lot of those just yet. 10 gigabit networks will be super fast, appropriate for certainly for backbone networks, even being twisted pair. A lot of times you'll see fiber optic, but this is definitely a viable alternative because of the speed. The cost side of things certainly makes it more attractive than fiber optic, so that's a good part of it. Going to require probably Cat 6 or Cat 7 cabling. Again, maximum segment length of 100 meters. Really fast, low cost, so it makes it very attractive relative to fiber. On fiber optic, again, that's what I was saying earlier, Ethernet is not tied to a specific type of medium. It's a signaling, it's a way of sending ones and zeros across a medium, so you can send it across fiber optic as well. And there's several different fiber optic standards. 100 base FX, which is, again, a similar format. The 100 stands for 100 megabits per second. Fiber optic cabling, multi-mode fiber containing at least 2 strands. Makes it half duplex. One strand receives, one strand sends. To end up full duplex between the two. 412 meter segment length. So because now you've got significantly more distance that you can transmit. So if you have a need for your nodes to be further apart, you may have to not use twisted pair. You may have to go with more expensive equipment, more expensive cabling in order to be able to do that, but you can. So full duplex mode uses both strands to send and receive and increases the segment length. One repeater maximum. And gigabit Ethernet, again, you have a gigabit throughput. Uses, I believe it's smaller wavelengths, so you actually end up with longer segments. With single mode fiber, up to 5,000 meters per segment. With multi-mode, which is not as efficient, that's where, remember, that's the wider mode that we talked about last week, or a couple weeks ago, where the center core is a little bit wider, so you end up with more refraction of the laser, or the light signal. So because of that, the distance on it isn't quite as great, but it's still pretty good, 550 meters. It's longer than you get with using twisted pair. Again, one repeater between segments. It's a good choice for networks that have a need for pretty good sized backbones. Distances between various sections of the network. 1,000 base SX, so it's again a gigabit Ethernet, but on a different type of fiber. Uses multi-mode fiber optic, which is less expensive than single mode. Uses short wavelengths rather than long wavelengths. The LX was for long wavelengths. SX has short wavelengths. As a result, it can transmit more data over the same period of time. So the maximum segment length depends on has several dependencies: the fiber diameter, the bandwidth to transmit the signals. 1,000 base SX, highest frequency of multi-mode fiber signal, higher modal bandwidth. Multi-mode fiber carries signal reliably longer. 50 micron fibers, about 550 meters. 62.5 micron fibers, 275 meter maximum length. One repeater between segments, best suited for shorter network runs. When you start getting into some of these others, and a lot of this is exactly the same stuff, but where it starts to change is, depending on some of the subtle differences, are, let's see, down here. This particular one, 10 gigabit base LR and 10 gigabit base LW. You can get up to 10,000 meters on that particular one. I'm not going to ask you for questions about specific ones, but I do want you to look at fiber, and when you see fiber, recognize that you can transmit much further distances. Speed-wise, over copper, you're approaching some of the same speeds and getting to some of the same speeds as you can get with fiber optics, but there is a distance limitation that you're running into on copper. Using 10 gigabit based ER and EW, you can get up to 40 meters, so 25 miles you can get up to. So they give you a nice table here that kind of gives you a breakdown of the different standards that they list. For the most part, I want you to be familiar with these right up in here, the different copper the copper ones. When you see 10 base T, you should know that that's a 10 meg network running on twisted pair. Same thing with 1000 base T, 10 gigabit T, base T, etc. As far as the fiber ones, like I said, I want you to be aware that they provide you with better distances that they can transmit between nodes, and that if you go with single mode fiber, you tend to be able to transmit further than with multi-mode, all else being equal. Okay, so any questions? You guys never ask questions. Ethernet frames. Think of it's like a packet, but it's operating at layer 2. So a frame is a packet that's operating at layer 2. And there's different types. There's these different standards of Ethernet. For the most part, we use Ethernet 2, or the DIC standard. Which I believe is DEC, Intel, and Xerox. But they're all just basic different configurations of the frame. Different parts of the frame, how it's laid out, and what the different parts mean. There's a lot of similarities between the two. I'm not going to ask you a question about how many bits is a particular, the header of this. I'm not going to ask you that type of stuff. But you should be able to see some of the similarities of it and say it has to have a sequencing bit to be able to tell you the order that these things came in. You should be able to identify that. So the frame types differ slightly, but for the most part they tend to have a lot of similarities. There's no relation to topology or the cabling characteristics, so it doesn't matter whether it's over fiber optic or it's over copper, it doesn't matter. And they talk about framing independent of higher level layers. In other words, it doesn't care whether you're using an IP or TCP IP, IPX, SPX, it doesn't care about the higher level protocols. It's totally ignorant of those. So, using and configuring frames, ensure all devices use the same correct frame type. In other words, if you happen to be on a network that's using one particular frame type, say this very top one right here, if the rest of the nodes don't understand that, you can't communicate. You all have to be talking the same language. I'll tell you in a minute why that's irrelevant for the most part now, but for the most part we use Ethernet 2. Frame type configuration you can set oftentimes through the NIC configuration software, but for the most part they auto-detect which frame type is being used anyway. So very rarely you're ever going to have to worry about it. It's going to determine which type is used on that network. May be important for troubleshooting, but it's just really unlikely. Some of the common frame fields, a preamble, something to start the beginning of a frame that's going to tell whatever device that you're sending it to, a hub, switch, router, etc., where the beginning of a frame is. A start frame delimiter, a 14-byte header, a frame check sequence, so did that frame get there intact as it was sent, and then the frame size range, so your actual data itself, your content, your payload. Larger frame sizes result in faster throughput for the most part. That's true on a fault-tolerant network, a network that doesn't have problems with it. So good cables that are terminated properly, not a lot of interference. If you do have some of those problems, that's not necessarily the case. Why? Because if you get a packet that gets dropped, you have to rebroadcast it. Well, the bigger those frames are, the more likely you're going to have, when you have those types of problems, the more likely you're going to have to rebroadcast more and more frames. So it becomes an issue in that type of environment. But for the most part, our networks are pretty good anymore. So for the most part, larger frame sizes do tend to result in faster throughput. Let's see. Ethernet 2, developed by DEC, Intel, and Xerox, sometimes referred to as DICs. It's now standard by IEEE. Contains a 2-byte type field. And the reason that that's important, that allows that particular frame to identify the network layer protocol that's being used. The reason that's important is it allows it to support all different types of higher level protocols. Instead of just running one type of protocol across your data link layer, you can run various types of protocols, higher level protocols, at the same time without interfering with each other. Ethernet snap frame type, very similar, less room for data, so it doesn't tend to do this, it doesn't tend to be used as much as the DIC standard with Ethernet 2, but it has the same capability of being able to identify the network layer protocol that's being used. But again, it doesn't tend to get used that much. So here's kind of an example of an Ethernet frame. Preamble, where's the beginning of the frame going to start, type information. Destination address, where it's going to, where it's coming from, what's the protocol, IP, etc. Your actual data itself, and your ability to error check. Chapter finishes up talking about power over Ethernet. Everybody heard of power over Ethernet? Anybody use it? I have to tell you, I'm not a big fan of putting power near data lines, but you know, there's some applications for it. The idea is that you occasionally end up with devices that you need to be able to locate in remote areas that don't necessarily have power conveniently located, so you don't have a plug nearby. You can potentially provide power across your data lines, or not your data lines, but the extra lines of your network cable that aren't being used. You can use those to provide power to those devices. And that's the idea behind power over Ethernet. Now that's true for all those cables, or all those Ethernet standards that we were talking about, copper Ethernet standards that we were talking about, up until we got to gigabit Ethernet. Gigabit Ethernet used all 4 wires. But they actually have, I've never done it, but as I understand it, they actually have workarounds for that as well. With gigabit Ethernet, you can still provide power over Ethernet. But it is a way to provide power to devices in remote areas where you can run a data cable, but it's not necessarily convenient to be able to run a power port or power outlet. So to be able to do that, you have to have a device that supports it, and you have adapters that can allow you to adapt what you've got going on. So summary, we talked about physical and logical topology. Try to draw a distinction between the two. Remember, they don't have to be the same. In fact, they usually aren't. For the most part, you end up in today's, in a lot of today's installations, you end up with a physical star topology or a hybrid topology, certainly with star being a major component of it, and then a bus topology as far as the logical topology. We talked about network backbones, oftentimes going to be fiber optic, or certainly Cat6 or Cat7 cable. Some of them will support really high-speed bandwidth. Why? Because we're usually linking together multiple LANs, so they're going to be pumping through a lot of data. We talked about switching and some of the different types of switching, packet filtering versus circuit switching, packet switching versus circuit switching. And then I finished up that chapter talking about Ethernet and Ethernet across copper versus fiber optic. So I think that's a pretty good chapter. Go back and read it. If you have any questions, shoot me an email or see me after class or see me during the break.